So let's take a look at the dot product. Now the dot product is one of the ways you can multiply two vectors. And so the result is not another vector, but instead you get a scalar or some constant value. So let's say for the dot product we have one vector A, which has the components x1, comma y1, comma z1, and the other vector is B, and it has the components x2, comma y2, comma z2. Now, when you do the dot product, you take A and multiply by B, and how you do this is you multiply the same components, so the same x components, we take x1 times x2, and then we add the same y components being multiplied. So add y1 times y2, and then add z1 times z2. And if you have vectors, if you're multiplying vectors that don't have three components, they just have two x and y, then you don't have to worry about the z. So let's say for number 1 we have to find the dot product of A times B, and we're given that A's components are 4, negative 1, and B has 3, 6 as its components. So once again, A times B, in order to find the dot product here, we're going to multiply the similar components. So the x components are 4 times 3, which give us 12, and then we add when we multiply the y components together. So negative 1 times 6 gives us negative 6. So the dot product gives us a value of 12 minus 6, or 6. So for number 2, A's components are 5, 0, negative 2, and B's components are 3, negative 1, 10. So once again, in order to find the dot product here, A times B is going to equal, we're going to multiply the same x components together, so 5 and 3 gives us 15, and then plus the y components, 0 and negative 1, that's just 0, and then plus the z components, so negative 2 and 10 gives us negative 20. So when we add these two together, we'll get 15 minus 20, or negative 5, as the final answer. So for number 3, we have A equals I minus 2j plus 3k, and B equals 5i plus 9k. So notice both of these vectors are in its unit vector form, where we have the variables I, j, and k, but what we can do here is turn it back to its standard component form. So if we were to write vector A in component form, notice I goes with the x component, and the coefficient in front of I is 1, so we can just put 1 for the x component. Negative 2 is in front of j, so that will be our y component, and 3 is in front of k, so that is our z component. Now for vector B, its components are, well, 5 goes with in front of the I, so that will be the x component. Notice there is no j, so that means our y component is 0, and then 9 is in front of the k component, so that will be our z value, or z component here. So now in order to find the dot product, we're going to multiply similar components. So 1 times 5 gives us 5, plus negative 2 times 0, that's 0, and then plus 3 times 9, which gives us 27. So 5 plus 27 is obviously 32, and that is the final answer. So now let's say we have two vectors. So we have vector A and we have vector B. And let's say we're trying to find that angle in between those two vectors, that theta value. So in order to do that, we have to remember the formula where cosine of theta is going to equal to the dot product of A times B over the magnitude of A times the magnitude of B. And so if we were to isolate theta to find that angle, theta is going to equal inverse cosine, or arc cosine, of dot product of A times B over the magnitude of A times the magnitude of B. So for number 1, we have to find A times B, given that the magnitude of A is 12, the magnitude of B is 15, and the angle between A and B is pi over 6. So we have to obviously use the formula here, so cosine of theta is going to be equal to, once again, the dot product of A times B over the magnitude of A times the magnitude of B. So we already know what the magnitude of A is, we already know what the magnitude of B is, and we need to find A times B, and we also know what the angle, or theta, is, pi over 6. So if I were to plug all those into the formula, we get cosine of pi over 6 equals A times B over the magnitude of A, which is 12, times the magnitude of B, which is 15. So 12 times 15 is 180, and if I go ahead and multiply that to the other side, we get A times B equals 180 cosine of pi over 6. Now cosine of pi over 6, or cosine of 30 degrees, is going to give us the square root of 3 over 2. So A times B equals 180 times the square root of 3 over 2. 180 over 2 simplifies to 90. So the final answer, a times b, or the dot product, is going to equal 90 times the square root of 3. So for number 2, let's go ahead and find the angle between the vectors a and b. So a is 3, 4, and b's components are 5, 12. So once again, the formula here, cosine of theta, or cosine of the angle, is going to be equal to the dot product of a times b over the magnitude of a times the magnitude of b. So let's go ahead and first find the dot product of a times b. So obviously, a times b equals, we're going to combine or multiply similar components. So we get the x components, 3 times 5, which gives us 15, and then plus, when we multiply the y components, 12 times 4, or 48. So that's going to give us an answer of 63. So now let's find the magnitude of a. So remember, the magnitude of a is going to be equal to the square root of x squared, the x component squared, plus the y component squared. So if we use that formula here, we'll take the square root of 3 squared, which is 9, plus 4 squared, which is 16, and so that gives us the square root of 25, which obviously is 5. So that is going to be the magnitude of a. And for the magnitude of b, we're going to use the same formula, the square root of its x component, which is 5, so 5 squared will be 25, plus 12 squared, which is 144. 25 plus 144 gives us 169, and the square root of 169 gives us 13. So that is the magnitude of b. So now when I plug into the formula here, cosine of theta is going to equal the dot product a times b, which we found to be 63. And then we take that over the magnitude of a times the magnitude of b. So the magnitude of a is 5, and the magnitude of b is 13. So 5 times 13 gives us 65. So in order to find theta, we're going to take the inverse cosine, or arc cosine, of 63 over 65. Now let's go ahead and put our answer in degrees. So make sure your calculator is in degree mode, or if you calculate it in radians, then you can multiply it by 180 over pi. And that should give you an answer of around 14 degrees as the angle in between a and b. So for number 3, let's find the angle in between a and b. And so a is represented by j plus k, and b is equal to I plus 2j minus 3k. So given the vectors are in unit vector form with the I, j, and k variables, let's convert it back to regular component form. So let's go ahead and turn vector a into component form. So a, now notice there is no I value here, so the I value is directly related to the x component, and so the x component is 0 since there is no I. Now since there's a 1 as a coefficient in front of j, our y value or y component is going to be 1, and there's a 1 in front of the k, so our z component is going to be 1 as well. Now for b, vector b, there's 1 in front of the I, so that's going to be our x component. There's a 2 in front of the j, that's our y component, and negative 3 is going to be our z component because that's in front of the k value. And so now, remember the cosine of theta is going to equal a times b over the magnitude of a times the magnitude of b. And so let's go ahead and find the dot product of a times b first. So a times b is going to equal the x components being multiplied here, so 0 times 1 gives us 0, plus the y components, 1 times 2 is 2, and then plus the z components, negative 3 times 1 is negative 3. So that will give us an answer of 2 minus 3, or negative 1. Now in order to find the magnitude of a, since we do have 3 components, x, y, and z, we're going to take the square root of x squared, which is 0, plus y squared, so 1 squared is 1, and then plus z squared as well. So our z component squared is also 1. So that will give us the square root of 2. And the magnitude of b is going to be equal to the square root of x squared, which is 1, plus the y component squared, so 2 squared is 4, and then plus the z component squared, so negative 3 squared is 9. And that will give us the square root of 14. So filling in the information to the formula, we get cosine of theta is going to equal to the dot product of a times b, and we got negative 1 for that. So I'll replace that with negative 1 over the magnitude of a, which is the square root of 2, times the magnitude of b, the square root of 14. And when I multiply those two together, we'll get the square root of 28. So in order to find the angle, let's just go ahead and inverse cosine, or arc cosine, both sides. So theta is going to be equal to arc cosine or inverse cosine of -1 over the square root of 28. And once again, we got to be in degrees mode, so this should give you a value of around 101 degrees. Now the relationship between two vectors A and B in terms of the angle between them can be classified into three different categories. Now the first one is orthogonal or perpendicular, they're basically the same thing. And that's when the relationship or the angle in between two vectors A and B is exactly 90 degrees. Now parallel is when it's either 0 degrees or it can also be a full 180 degrees between A and B, and neither is if it doesn't meet any of those other conditions. So the easiest way to find out whether two vectors are orthogonal to each other or perpendicular is if the dot product A times B equals 0. So this is the very first step. You need to check if A times B equals 0, because if it does, then you automatically know that it's orthogonal. Now if it doesn't equal 0, then you need to make the extra step of finding out what the angle actually is. And if you find out the angle is either 0 or 180 degrees, or 0 radians or pi radians, same thing, then you know it's parallel, and if it's none of those, then it's going to be neither. So for number 1, A is equal to -537 and B has its components 6, -8, 2. So the very first step into figuring out whether the relationship between vectors A and B is orthogonal or perpendicular is to find the dot product. So we take A times B. So once again, when we take A times B, we multiply similar components together and add them. So -5 or -5 times 6 gives us -30. And then we add the y components being multiplied, so 3 times -8, which is -24, and then plus 7 times 2, which is 14. And so that will give us a value of -40. So we know the dot product does not equal 0, so we know it cannot be perpendicular or orthogonal. So now we have to find what the angle is actually to see if it's parallel or if it's neither. So once again, cosine of theta is equal to A times B over the magnitude of A times the magnitude of B. So let's go ahead and find the magnitude of A first. So that is going to equal to the square root of the x component squared. So -5 squared will give us 25, plus the y component squared, 3 squared is 9, and then plus the z component squared, 49. And so that will give us the square root of 83. So now in order to find the magnitude of B, the same process here as finding the magnitude of A, we'll take the square root of the x component squared, so 6 squared is 36, plus the y component squared, 64, and then plus the z component squared, 2 squared is 4. So that will give us 40 plus 64, or 104, the square root of 104. And so if I plug into the formula, cosine of theta is going to equal to the dot product A times B, which we got -40. So we take -40 over the square root of 83 is the magnitude of A times the square root of 104, which is the magnitude of B. And so in order to find that angle, we can go ahead and take the inverse cosine or arc cosine of both sides. So we'll take the inverse cosine of -40 over the square root of 83 times 104, which gives us 8,632. And so in degrees, that should give you a value of around 116 degrees. 116 degrees does not equal 0 or 180 degrees. So we know that this is classified as neither parallel nor perpendicular or orthogonal. So for number 2, we have A, which has its components 4, 6, and B, which has components -3, 2. And so let's go ahead and see whether it's orthogonal or perpendicular by testing out the dot product first. And so A times B, the dot product, we're going to take 4 times -3 first. That'll give us -12, plus the y components being multiplied, so 6 times 2, which is 12. And so that gives us 0. And so right off the bat, since the dot product equals 0, we know that this is orthogonal or perpendicular. So for number 3, A is equal to 2i plus 6j minus 4k, and B is equal to -3i minus 9j plus 6k. So let's go ahead and first test out the dot product. But before we do that, let's change the unit vectors into its component form. So A in its component form is going to be equal to 2 is in front of the I, so that is going to be our x component, 6 is in front of the j, so that's our y component, and negative 4 is in front of the k, so that's our z component. Now for b, in order to turn it to component form, negative 3 is in front of our I, that's going to be the x component, negative 9 is going to be the y component, and 6 is the j component. So in order to find a times b, once again, let's multiply the similar components. So 2 times negative 3 gives us negative 6, plus 6 times negative 9, or negative 54, and then plus negative 4 times 6, which is negative 24. And so that will give us an answer of negative 84 as the dot product. So negative 84 does not equal 0, so we know that this is not perpendicular or orthogonal. So let's go ahead and find the actual angle. So cosine of theta equals a dot product, a times b, and I'm just going to go ahead and substitute negative 84 already, since we already know what a times b is equal to. Now over the magnitude of a times the magnitude of b. So in order to find the magnitude of a, take the square root of the x component squared, so 2 squared, which is 4, plus the y component squared, 36, plus the z component squared, 16. And so that will give us the square root of 16 plus 4 is 20, so then 56. Now in order to find the magnitude of b, we're going to take its x component squared, so 9, plus its y component squared, 81, and then plus its z component squared, 36. And that should give us a value of 90 plus 36, or 126. So let's go ahead and plug those numbers in. So we get cosine of theta equals negative 84 over magnitude of a, which is square root of 56, times the magnitude of b, which is square root of 126. And that will give us the square root of 7,056 when we multiply them. So theta is going to equal to the inverse cosine of that value, and so that should give you a value of exactly 0 degrees. And since it is 0 degrees, we know the relationship between vectors a and b is parallel. So now on to the next topic here. Direction cosines are actually just going to be the cosines of the direction angles. So let's say we have vector a, and it has its components a1, comma a2, comma a3. Then we have to know the simple formula where cosine of alpha is going to be equal to the unit vector a1 over the magnitude of a. Cosine of beta is going to be equal to a2 over the magnitude of a, and cosine of gamma is going to be equal to a3 over the magnitude of a. So those are going to be the direction cosines. Now in order to find the direction angles, those direction angles are just alpha, beta, and gamma, so all we have to do is isolate those angles and inverse cosine both sides to get the angles. So for number 1 we have the components 3, 4, 5, and let's go ahead and find the direction cosines and the direction angles. So the first thing we have to do is find the direction angles, and so let's go ahead and just call this vector A. This will be equal to vector A. And so let's go ahead and find the magnitude of vector A. So that is going to be equal to the square root of the x component squared, so 3 squared is 9, plus 4 squared, 16, and then plus 5 squared, which is 25. And so that will give us the square root of 50. And if you want to simplify also, and so you can also simplify square root of 50 into 5 times the square root of 2. And so let's go ahead and write the direction cosine. So cosine of alpha is basically going to be equal to the x component, so 3, over the magnitude, so 5 times the square root of 2. Cosine beta is going to be equal to the y component, which is 4, over the magnitude, 5 times the square root of 2. And then cosine of gamma is going to be equal to 5, the z component, over 5 times the square root of 2. And that can be simplified into 1 over the square root of 2. So those are going to be the direction cosines. Now in order to find the direction angles, we go ahead and isolate each angle. So in order to isolate alpha, we'll just go ahead and inverse cosine both sides. So alpha is going to equal to the inverse cosine of 3 over 5 times the square root of 2. And so in degrees, that should give you around 65 degrees. Now in order to find beta, we can go ahead and isolate it. So the same process here, inverse cosine of 4 over 5 times the square root of 2. And so that should give you around 56 degrees. And then finally for gamma, we go ahead and isolate it. So that's going to be equal to the inverse cosine of 1 over the square root of 2. And that should give you exactly 45 degrees. Because cosine of 45 degrees, or cosine of pi over 4, is exactly square root of 2 over 2, or 1 over the square root of 2. So those are going to be the direction angles. So let's go ahead and find the direction cosine, direction angles for number 2, 2i plus 3j minus 6k. So first thing, let's go ahead and turn that into component form. So let's just go ahead and name that vector A, and let's turn that vector A into component form. So we can rewrite it as 2 as the x component, 3 as the y component, and negative 6 as the z component. And so in order to find the magnitude of this vector, we go and take the square root of the x component squared, so 4, plus 9, which is 3 squared, and then plus negative 6 squared, or 36. So then we get the square root of 49, we add them, and so that will give us 7. So that is the magnitude of vector A. Now cosine of alpha is going to equal to the x component, which is 2, over the magnitude of A, which is 7. Cosine of beta is going to equal to the y component, 3 over 7. And cosine of gamma is going to equal to the z component, negative 6 over 7. So those are going to be the direction cosines. Now in order to find the direction angles, let's go ahead and isolate alpha. So that is going to equal to the inverse cosine of 2 over 7. I'm just going to go ahead and write the formulas for all of them. Beta is going to equal inverse cosine of 3 over 7. And then gamma is going to equal to the inverse cosine of negative 6 over 7. And I'll go ahead and put all these in degrees. And so alpha is going to be around 73 degrees. Beta is going to be around 65 degrees. And gamma is going to be around 149 degrees. So those are going to be the direction angles of the given vector A. So now moving on to projections, we have two types of projections, scalar and vector. So scalar is also known as component. So it can be written as the component of B onto A. And the formula for that is going to be A times B, or the dot product of A times B, over the magnitude of A. And so in order to calculate now the vector projection, which is write it as the projection of B onto A, we just take the regular scalar, or the component, A times B over the magnitude of A, and now we multiply it by the unit vector of A, so A over the magnitude of A. And that's how you find the vector projection. So for number 1, let's go ahead and find the scalar projection and vector projections for A, which has the components 3, negative 4, and vector B, which has the components 5, 0. So once again, the scalar projection, also known as the component of B onto A, is going to be equal to the dot product of A times B over the magnitude of A. So let's go ahead and find the dot product first. So A times B is going to be equal to, let's go ahead and multiply the similar components. So the x components 3 times 5 gives us 15. And then we add when we multiply the y components, and negative 4 times 0 is 0. So the dot product gives us 15. And the magnitude of A is going to be the square root of the x component squared plus the y component squared. So 3 squared 9, negative 4 squared 16. And so that will give us the square root of 25, or 5. So that is going to be the component, or the scalar projection, is going to be equal to 15 over 5, which gives us 3. Now in order to find the vector projection, we're just going to go ahead and take the component projection, what we got for the answer. So we take 3 and multiply it by the unit vector of A, which is obviously A over the magnitude of A. So we take 3 multiplied by the vector A, which is in its component form 3, negative 4, over the magnitude of A, which we found to be 5. So if I were to rewrite this, we can rewrite it as 3 over 5 times the vector 3, negative 4. And since this is like a constant or a multiple, we can go ahead and multiply that inside the vector. So if we distribute the values, we'll get the vector of 9 over 5, comma, negative 12 over 5. And so that is going to be the vector projection. So for number 2, let's find the scalar projection and vector projection for A, which equals I plus k, and B, which equals I minus j. So once again, the component or the scalar projection of B onto A is going to equal to the dot product of A times B over the magnitude of A. So let's go ahead and write A and B in terms of their component forms. So if I were to write A in component form, now 1 is in front of the I, or it's the coefficient in front of I, so that will be our x component. There is no j component, which means our y values, or y component is 0, and there's 1 in front of the k, so our z component will be 1. Now in terms of B here, in component form, we have just 1 as a coefficient of I, so that's going to be our x component. We have negative 1 in front of j, so that will be our y component, and there's no k, so 0 will be our z component. Now let's go ahead and find the dot product of A times B. So A times B is going to be equal to 1 times 1, which gives us 1, plus 0 times negative 1, which is 0, and then plus 0 times 1, obviously another 0. So the vector, or sorry, the dot product yields 1. Now in order to find the magnitude of A, let's go ahead and take the square root of the x value squared, so 1 squared is 1, plus 0 squared, and then plus 1 squared. So our magnitude will be the square root of 2. And so the component, or the scalar projection of B onto A is going to be equal to A times B, which is 1. 1 we got as our dot product, over the magnitude of A, which is the square root of 2. So that is going to be the scalar projection. Now in order to find the vector projection, we go ahead and multiply by the unit vector of A. So we take vector A, which is noted as 1, 0, 1, and over the magnitude of A, which is the square root of 2. So to simplify, square root of 2 times square root of 2 gives us 2. So we get 1/2 times the vector 1, 0, 1. And so we can go ahead and distribute that inside the vector. So we get 1/2, 0, and 1/2. Now, because the problem was given to us in terms of I, j, and k, in terms of those unit vectors, it's probably a good idea to write the answer in terms of I, j, and k as well. So the way we write this is we have an x component of 1/2, so that goes with the I. So we get 1/2 I, plus 0 is our j component, or sorry, our y component. So that will go 0 times j, and then k goes with our z component, and our z component is 1/2. So we get plus 1/2 k. Since 0 times j is just 0, we can go ahead and eliminate that. And so we get 1/2 I plus 1/2 k. We go ahead and factor out that 1/2. So we get I plus k. And so the final vector projection of B onto A is going to be equal to I plus k over 2. So on to the next topic. The main application for projections is going to be calculating work. So there are two main formulas for work here. Work can either equal the force vector times the distance vector, or work can equal the magnitude of the force times the magnitude of the distance, or in other words, just the distance traveled, times cosine of the angle theta. So for number 1, let's say constant force with vector representation F equals 10I plus 18J minus 6K moves an object along a straight line from the point 230 to the point 4915. Find the work done in Newton meters or joules. So right off the bat, the most obvious formula we have to use here is work equals the force vector times the distance vector, because we're already given the force vector here. Now we can rewrite it in component form here. So let's say the force is going to be equal to 10, 18, and negative 6 in component form. And so let's go ahead and find the distance vector now. So we're given two endpoints here. And so if we connect these two endpoints with a line, we get a line segment. And in my previous video, we learned how to represent a line segment with a vector. And so the simple formula for that is the distance vector is going to be equal to x2 minus x1, comma y2 minus y1, and then comma z2 minus z1. And so that will give us a representative distance vector. So let's go ahead and say 230 is our first point, and 4915 is our second point. So the distance vector here is going to be x2, which is 4, minus x1, which is 2. So 4 minus 2 gives us 2, comma y2 minus y1, so 9 minus 3 gives us 6, and then comma 15 minus 0, which gives us 15. And so 15 minus 0 gives us 15. So using this formula, given the force vector and the distance vector, we can go ahead and take the dot product of the force vector times the distance vector. So using the dot product, we can multiply the force vector times the distance vector. So once again, when we calculate that, we're going to multiply similar components. So we take the x components 10 times 2, we get 20. So then plus 18 times 6, so that's going to be 108. And then plus negative 6 times 15, or negative 90. And so that will give us a value of 38. And so the work done, the total work done, is going to be 38 Newton meters, which is also known as 38 joules of work. So now for number 2, a woman exerts a horizontal force of 25 pounds on a crate as she pushes it up a ramp that is 10 feet long and inclined at an angle 20 degrees above the horizontal. Find the work done on the box. So if I were to draw this a little bit, we have a ramp that is 10 feet long, 10 feet, and it is inclined at an angle 20 degrees above the horizontal. Now, a woman exerts a horizontal force of 25 pounds on a crate, so a horizontal force of 25 pounds, as it is pushed up the ramp. So now, if we find the work done here, the formula we have to use here is work equals the magnitude of the force times the magnitude of the distance, or just the distance traveled, times cosine of theta. And the reason we know that is because we're given an angle, we're given the magnitude of the force, and we're given the distance traveled. So we can just go ahead and take the magnitude of the force, which is 25 pounds, and then multiply it by the distance, which is 10 feet, and then multiply it by cosine of the angle of the ramp, which is 20 degrees. And so the total work done here, you should get around 235. And since we're using pounds and feet, the units for work in this case are going to be in terms of foot-pounds. So 235 foot-pounds of work are being done on the crate for it to be pushed up the ramp.